In this video, we're going to look at a type of bonding called covalent bonding. Covalent bonding is considered the sharing of electrons evenly between two atoms. And compounds that form covalent bonds tend to be between nonmetal and nonmetal elements. These compounds typically have lower melting points and boiling points, and are liquids or gases at room temperature. And because they are covalent bonds, they tend to not be soluble in water and therefore tend to be very poor conductors of electricity. When we're looking at substances that form covalent bonds, there are two really important things that we need to kind of address when we're looking at these substances. First off, the bond length, and secondly, what kind of covalent bond, because there are subcategories of covalent bonds that can be formed. And we typically refer to those as pure versus polar covalent bonds. And we will use the periodic trend electronegativity to help us discern which kind of covalent bond that happens to be. So let's take a look at bond length. So bond length is essentially determined by the distance between two nuclei of different atoms, which achieves what we call the lowest potential energy. So if you could write a graph where the y-axis is the energy or potential energy between two atoms' nuclei, and the distance between those atoms on the x-axis. It turns out, in this particular graph, they're showing the distances between the nuclei of two hydrogen atoms. And when you have the distance of the two hydrogen atoms' nuclei as pretty far apart, shown in this particular portion of that graph, the potential energy tends to be on the scale of 0. However, the closer and closer you move those nuclei, shown in this second graph, or second part of this graph, the potential energy starts to go down in value. And eventually what will happen is you will plateau and turn around that energy level, and it will start to go positive again. So we're going to go all the way down, and then it will come back up. The distance between these two nuclei at the bottom of this curve is considered the most optimum distance for forming that particular type of covalent bond between those two types of elements or atoms. As you push closer and closer the nuclei of atoms, the potential energy dramatically increases, so much so that it would not be energetically favorable for them to be that close in distance. So what we tend to do is determine this particular value for each type of covalent bond between different types of atoms. Over here on the right-hand side are some common bond lengths that have been determined between other types of atoms. So the bond length between a carbon and a carbon atom is 1.54 angstroms. And angstroms is another form of measuring distance that is equivalent to the picometer that you see down here on the x-axis of that graph. Carbon nitrogen, 1.43. Carbon oxygen, the same distance. Hydrogen hydrogen, which we've already seen as 0.74, and then carbon hydrogen as 1.09 angstroms. So that the single covalent bond that you see between all of these types of atoms, the one that you can see out of this group that has the longest distance between the two atoms themselves, is the carbon-carbon, and the one that has the shortest distance between the two atoms is the hydrogen-hydrogen. There is a scale or a table in your textbook that gives you average distances of atoms between atoms of different types of elements. And this table is table 7.3. The second thing that we want to look at when it comes to covalent bonds is whether or not they are considered pure or polar. What is the difference between a pure covalent bond and a polar covalent bond? Well, a pure covalent bond is still electrons being shared between two atoms, but they're shared in an equal fashion. More often than not, a pure covalent bond tends to be between two of the same type of atoms. For the example that I showed you here was chlorine bonded to chlorine. However, that is not always the case, and I will show you in just a few seconds or a few minutes how to determine whether or not a bond is considered pure versus polar mathematically. A polar covalent bond, however, is still electrons being shared, but they're being shared unequally. An example of that would be the sharing of electrons between a hydrogen and a chlorine atom. So how do you know by just looking at atoms or a covalent bond whether or not something is pure or polar? This comes with a little bit of experience, but there is also a mathematical way for you to determine that and not have to memorize things or use experience that you may not have at the moment. So one of the things is we can use the values of the periodic trend of electronegativity, and we can use that to determine the degree of polarity, whether it be polar or pure covalent bonds, and we can actually use that to even say if a bond is more polar than another. So the periodic trend of electronegativity is found in figure 7.6 in your text, and the values that you see here is on a scale of 0 to 4, and it's called the Pauling scale. And the Pauling scale says that the closer you are to 4, the more electronegative you are. The closer you are to 0, the less electronegative you are. And if we just remind ourselves of what electronegativity is this is the value of, or the degree of how much does an atom want to gain an electron. And so you would expect things like atoms that are over in the far group here that's group 7 to really, really want electrons, compared to atoms that are over here in group 1 that really don't want to take an electron but rather give away electrons. And so how do you do this? Well, we use this electronegativity scale to determine whether a bond is pure covalent, polar covalent, and we can even use this mathematical scale to determine if something is ionic as well. And so this is how it works. We take the difference in the electronegativity values of the first atom to the second atom, and we put that in absolute value. So for instance, if I want to know what the difference in electronegativity are for hydrogen to chlorine, this is how I would do that. Well, I would determine the difference in electronegativity by taking the absolute value of the electronegativity of hydrogen, which if we go back to our electronegativity periodic table scale, hydrogen is 2.1. And we will subtract from that the electronegativity value of chlorine. And go back there, chlorine is 3.0. We take that absolute value. And this ends up being 0.9. That is the difference in electronegativity. And so we take this value that we have now calculated and we look at where does it fall in this chart. So if the value is less than 0.4, you're considered pure covalent. If it is in between 0.4 and 1.8, which means it can be equal to 0.4 all the way through equal to 1.8, you're considered polar covalent. Or if it is greater than the value of 1.8, you're considered ionic. Well, this value ends up being right in the middle of 0.4 and 1.8 of a 0.9, and so we call this particular bond a polar covalent bond. So let's practice this a couple of times. Again, you need to have the electronegativity periodic table scale as a reference. And so let's try this. So let's determine the type of bond that forms between each of the following atoms. So for part A, it's nitrogen and hydrogen. So we'll take our difference in electronegativity as the absolute value of nitrogen. Nitrogen happens to be 3.0. And we're going to subtract hydrogen's value, which is 2.1. And that ends up being 0.9. And that tells us, because it's 0.9, we call this polar covalent. Let's determine the type of bonding between carbon and oxygen. Carbon has a value of 2.5. And we're going to subtract oxygen, which is the value of 3.5. This then gives us an absolute value of 1.0, again, polar covalent. What about calcium and chlorine? Calcium happens to have a value of 1.0 for its electronegativity, but chlorine has a value of 3.0. Absolute value of this is 2.0, higher than 1.8, which puts us in the category of ionic. So this is how you determine whether a bond would be pure covalent, polar covalent, or ionic. There is also an additional piece of information that this the electronegativity values allow you to be able to do as well. And that is determine which atom, if you're going to have a polar covalent bond or an ionic bond occur, which atom will the electrons tend to spend more time with? Specifically in the covalent bond, because you're sharing the electrons, it turns out that the electrons will spend more time with the atom that is most electronegative. And so if that is true, if you look at this is nitrogen and this is hydrogen, between the bond between nitrogen and hydrogen, the nitrogen has a higher electronegativity, so therefore the electrons will spend more time with the nitrogen. And we use a specific little indicator or a little drawing to determine or write that in a bond. So we might write the bond and it looks something kind of like this. So we'll write nitrogen with the bond and hydrogen. And we will say, since the electrons, which are negatively charged, hang out with nitrogen more often, then it will have a partial negative charge, while hydrogen will have a partial positive charge. For the next problem, carbon to oxygen, you can do the same thing, but this time the oxygen has a greater electronegativity than carbon, so the oxygen will have a partial negative and the carbon a partial positive. We don't write calcium and chlorine with bonds like we saw for the polar covalent bond, but we can determine which will become the cation and anion using this same method, and that is the one that has the higher electronegativity will become the anion out of the two ions that form that compound. So calcium will be a plus charge and chlorine will be minus charge. And in fact, calcium likes to give away 2 electrons. And so you'll end up getting a calcium 2 plus, and then you'll end up having 2 chlorine atoms that both become negative charged to form a compound that would be called calcium chloride. Okay, this is the end of our covalent bond video. Look for our next videos on how to take ionic substances and covalent substances and start to draw structures with those particular compounds.